Okay, we're picking up in Chapter 2, Part 4, and we're going to start off with some sample problems of acceleration. Our first one, we have a cheetah can obtain a speed of 72 kilometers per hour from a standing start in just 2 seconds. What's the average acceleration? So we know we're looking for average acceleration. Okay. He can obtain a speed of 72 kilometers per hour from a standing start. So he's starting off standing still, not moving. But then he reaches 72 kilometers per hour. And he does this in a time of 2 seconds. Okay, well, we have kilometers per hour, and we're not told what unit, so we just know that our time unit has to be squared for acceleration. And that is one way you can tell whether you're given a quantity of acceleration or speed, in that the time unit will always be squared when you're dealing with acceleration, as opposed to when you're dealing with speed or velocity. So we need to convert this 2 seconds into hours. So what we're going to do is take our time of 2 seconds. We know that in 1 minute we have 60 seconds, and we know in 1 hour we have 60 minutes. So our seconds are going to cancel, our minutes going to cancel, and this will give us our time unit in terms of hours. So we have 5.56 times 10 to the minus 4 hours. Okay, we know that our average acceleration is delta V over T, which is VF minus V0 over T. So our final velocity is 72 kilometers per hour minus 0 kilometers per hour, and we're dividing that by 5.56 times 10 to the minus 4 hours. So you can see how these hours on the bottom will multiply with these hours right here, and that's going to give us our hours squared. So when we plug that into our calculators, our final answer is going to come out to be 1.3 times 10 to the 5th kilometers per hour squared as our acceleration. Okay, let's look at another one. So in this one, we have a horse accelerates from 4 miles per hour to 20 miles per hour. Okay. What is the horse's average acceleration in meters per second squared? So our horse is going from 4 miles per hour, so we know that is our initial is 4 miles per hour, and our final is 20 miles per hour. Now we're asked for our acceleration in meters per second, so we need to do some conversion. So let's start with our initial. We look up and we see that we have 5,280 feet in 1 mile, and in 1 meter we have 3.28 feet. We know in 1 hour we have 60 minutes, and in 1 minute we have 60 seconds. So quite a long conversion string. Let's see if we're going to get our meters per second. So miles will cancel, feet will cancel, hours will cancel, minutes will cancel. The only units I don't have canceled are meters per second. So when I plug this in, I should get 1.79 meters per second. Now we do the same thing for our final velocity. We have 5,280 feet in 1 mile. In 1 meter, we have 3.28 feet. In 1 hour, we have 60 minutes. And in 1 minute, we have 60 seconds. So we have 8.94 meters per second. And we're told that our time was 4 seconds. We are looking for our acceleration. So we know that the acceleration is final minus initial over time. So our final is 8.94 meters per second minus 1.79 meters per second. All that's going to be divided by 4 seconds, and our total answer will be 1.79 meters per second. So this problem gave us a bunch of conversion to practice, and you can see we had quite a long conversion string we were dealing with. Okay, let's do one other problem with acceleration. Here we have a child traveling 5 meters per second on a sled passes her younger brother. If her average acceleration on the sledding hill is 2 meters per second square, how fast is she traveling when she passes her older brother 4 seconds later? Well, we're told that initially she's traveling at 5 meters per second. We're given her average acceleration to be 2 meters per second squared. We want to know her final speed, and we're told that final speed we want to know is after 4 seconds. So we know that acceleration is final minus initial over time. We want to solve for VF, so we're going to multiply both sides by t. T's cancel. We have AT equals VF minus VI. Then we're going to add VI to both sides. VI's are going to cancel, and so we have VF equals AT plus VI. And I'm sorry, but I switched to VI instead of V0. VI is simply just V0, so I'm going to go ahead and put V0. I'm used to using VI for initial. Your book chooses to use V0 as initial. So now we can fill in with our numbers. VF equals our acceleration, 2 meters per second squared, times our time of 4 seconds, plus our initial is 5 meters per second. Now we got to make sure we have the right units because we're adding. So let's see. This 2 meters per second times 4 seconds, this second's going to cancel that second square. So therefore we're going to be left with meters per second plus meters per second, which we can do. And our answer is 13 meters per second. Okay. So that gives us some samples that we can practice with our acceleration. Okay, let's go back to our PowerPoint and where we left off. And on this slide, we're reminded again that acceleration is a vector quantity, and that's because velocity is a vector. Remember, vector quantities have both magnitude and direction. So in here we're seeing, in our first picture on the left, our speed's increasing. Okay? Notice when our speed's increasing, the acceleration vector and the velocity vector are pointing in the same direction. Now, in the picture on the right, however, notice the acceleration vector is in the opposite direction of our velocity vector. So therefore, we know that our speed's decreasing or we're decelerating. So we're slowing down instead of speeding up when those two vectors are pointing in opposite direction. And now I'm going to go back for a second and talk about acceleration due to gravity. It is a constant and it is denoted by a lowercase g. It is 9.8 meters per second squared. 9.80 meters per second squared. Okay, so what we know, as illustrated by this picture, for an object that has constant downward acceleration of 9.8 meters per second squared, its velocity is going to increase 9.8 meters per second for each second. As you can see, and I talked about this slide a little earlier, how each second we're taking this 9.8 and we are multiplying it by our second. So our first second, 9.8. Our second is going to be that 9.8 times 2. Third second is going to be that velocity at time 2 seconds times 3 seconds, and so forth. And that is going to give us a very linear graph. So when you're looking at the acceleration due to gravity and you plot velocity versus time, you will get a very nice linear graph. Now we also have some frictional effects that we have to consider. So the frictional effect that we usually consider is air resistance. Now if we could neglect air resistance, then everything would fall at the same rate, regardless of what mass it had. So the basic experiment is that if we would put a coin and a feather in a vacuum and drop them, the coin and the feather would fall at the same rate because we're taking out the air resistance. Because we know right now, if I gave you a feather and a coin and asked you to drop them, the coin is going to fall faster, and that's because of air resistance. Okay, the picture on the right shows an astronaut on the moon, and it's demonstrated using a hammer and a feather. Because the moon has no gravity, the hammer and the feather fell at the same rate when it was on the moon. We can look at the Leaning Tower of Pisa, and Galileo did the same experiment where he took rocks and he dropped them, and the rocks were of different mass. But he said if we took out the air resistance, then they would both be falling at the same rate. Okay, so this is going to end Chapter 2, Part 4.